what the probability is of an event occurring, what the probability is that my populations differ, and that sort of thing. Now, part of working out probability is to look at the distribution of a variable in a population, get some kind of distribution curve, and then we can work out what the probability of an event is. So in other words, I've got these plant lengths. I know the mean is 74 centimeters. I can answer the question now based on this distribution. If I go and measure in that population, what are the chances of picking up a plant that's 68 centimeters tall? The mean is 74, so it's quite a lot shorter than the mean. What is the probability that I can find a plant that is 68 centimeters? Well, if you look at this distribution here, I have 100 plants, 3 of them fell into the 68 class. Okay, so I can go along and say that the probability of a plant of 68 centimeters is 3%. The probability of a plant that's 74 centimeters is, how many plants did I have there? Can't remember now. But anyway, based on the number of plants in each group, as a percentage of the total, I can tell you what the probability is, okay? So without going into some of the complexities of probability, based on the population distribution and the mean and the standard deviation and so forth, I can work out what the probability of an event is. Okay. So when I talk about probability, I'm trying to say what is the probability of an event, or what is the probability that cultivars do in fact differ from one another, or whatever the case may be. Okay. So it starts becoming very complex, doesn't it? Are you still with me? I see a couple of hands. Okay. Right. And probability is very critical when it comes to statistics, and there are a whole lot of different probability distributions. They have different shapes, they have different values, and based on those we can determine the probability of an event. But I don't want to get into too much detail. I want to work on what we call the normal distribution. The normal distribution is what most statistics is based on. And what we do is we assume that populations are normally distributed, and if we can see on that graph, we can draw up a probability curve, and we can then use various maths to work out what the probability of an event is. The properties of the normal curve are you have a distribution that can accommodate continuous data to any level of precision. As the difference between the population mean and observations becomes smaller, y becomes larger, and until you can reach a point where theoretically you can reach a point where your sample mean and your population mean are the same. It's a curve that's symmetrical around the mean, okay? And on each side of the curve is an inflection point where direction changes from concave to convex, and a vertical line from this point to the baseline provides the second parameter, which is in fact, okay, which is your variation, okay, or your variance, or your standard deviation. So what we use in statistics is essentially the normal distribution. And we assume that all the populations that we are working with are normally distributed. And most of the statistics that we base our calculations on assume that the population that we have measured is normally distributed. And the importance of that I will mention again as we go along. What's also nice about the normal curve is that on either side of the mean, if you take one standard deviation unit, you're including 68% of the observations within that population. Now, we normally work on a 95% probability. We want to make sure that we're measuring 95% of the population. And under a normal curve, 95% observations are contained in the mean plus or minus 1.96 times the standard deviation. If we want a 99% picture of the population, we use the value of 2.58. Now, those of you who have done statistical analyses on large populations will know that number, 1.96. Don't you know? The t-value when you're working out LSDs or something like that, you know the value, large population, you use the value of 1.96. Okay? Why is that? Because 1.96 times the standard deviation includes 95% of the population. Okay? So that 1.96 that we use in a t-table is not a magic number. It's based on the variation within a population. Okay. So if I go 1.96 times the standard deviation on the other side of the mean, I've included 95% of the population. Okay, right. Again, that's an important statistic when it comes to measuring populations.